that question on the exam where you have a solid insulated sphere of uniform charge, that one's great because at least you know that the charge density is something that is relatively easy to express. I can take the entire charge, divide by the entire volume of the sphere, and that gives me an excellent expression for the charge density of the sphere. So when I look at that sphere, I could probably make some conjectures about how I deal with my Gaussian surface and not such. But there's been at least a dozen examples where the charge density is a function related to how far away from the center you are. There's been a bunch of these. We need to become good at using Gauss's law in the most basic way first. And I gave you this problem, and I gave you the one for a long, solid cylinder of similar charge density. And you have to figure out the electric field both inside and outside those objects as examples. So get a start on your homework, deal with the basic three, become proficient at them. I'm going to give you until day after tomorrow to have practiced the ones we've done in class. Does everybody understand? It'll be obvious when you look at your homework because it says, you'll see A, B, C, D, E, F, G on it. Those are the ones I want you to focus on the first three. And it's a point charge, a line of charge, and a sheet of charge. Repeat the work we did in class. Become proficient. Don't copy your notes. Try it from scratch. Because we need to come back to these. And we need to see how they behave in more meaningful ways. Today, we're going to take a bit of a digression. And we're going to talk about something that's relatively easy to discuss. We're going to talk about the difference between insulators and conductors. We'll take just one day to talk about this. The application of this is incredibly important. But today, we're going to introduce it, describe how they're different, and explain how they're going to be used on the exam. But I want you to start with just what you may know. So you guys have all made it through at least a little bit of a flow of electrons. Anything else you want to add to that? There are some other things. I'm not going to call on you until the arm actually leaves the table. All right, there we go. Yes, sir.
In this case, will we also be able to refer to temperature, or is that not something
So we know that there's another word, or at least another definition associated with insulator. Well, so what is an insulator in the context in which you're describing it?
It's a material that, I guess it'd be something that doesn't allow the transport of heat very well.
Right, it does not pass heat. Heat is the flow of energy, and specifically the flow of energy in order to raise or change temperature. So we can say that insulating materials do not allow for the passage of heat, or at least attempt to prevent the passage of heat. So sure, and these are related. Things that are good heat insulators generally are also particularly pretty good electrical insulators too. But the basic idea of an insulator is that if you have an insulating material and you place a charge on it, the charge stays where it's placed. So if you have insulators and you mix in charges, the charges will stay where they're placed. They won't move around in the insulator. They'll stay where they're placed. But they also don't allow for the passing of charge through the material. That's also true. Now, the truth is, of course, that if you push hard enough, you can push charges through any material. So all insulators can eventually be broken down. And that includes a vacuum. You push hard enough, you can push charges right through free space. But a vacuum is an insulator. So when we talk about insulating materials, we generally believe that when you place a charge on an insulating material, the charges won't move around from where they're placed. That's not true of conductors. Conductors have a few universal truths that supersede all formulas. I'm throwing this out here because if you don't take many notes in general, this is something to pay attention to. Conductors have a few truths that supersede all equations and formulas and laws. There's just some rules about conductors that are different. saying that a conductor is the opposite of insulator is really insufficient. That's not really what I want you to know. Conductors have interesting behaviors. First, conductors spread out on the surface of all conductors. Charges spread out on the surface of all conductors. But they don't do so in a haphazard way. You see, no matter what type or what material you have that's a conductor, no matter its shape, there is a universal truth to all conductors, and that is the electric field inside all conductors is zero. Period. Even if it's a charged conductor, the electric field inside the conductor is always zero. This is the most important truth about conductors, and it supersedes all laws, meaning you apply this idea first and then apply your law. And you may not understand why, but trust me, there are several different things we're going to talk about related to conductors that come right down to this. So the first thing I want to point out is that conductors generally have charges that will move freely around them. If you don't know conductors, look for things that are shiny. And although that's not always universally true, so the first thing you need to know is that no matter what charges are on the metal, the charges will always move to the outer surface of the metal. No matter what charges you have, let me say it again, excess charges always move to the outer surface of the metal. Excess charges always move to the outer surface of the metal. So if you have a solid piece of conductor, you won't find free charges in the middle of it. Now the reason that's true is because the electric field inside a metal is always zero. I want you to think about that for a minute. If I draw a Gaussian surface inside a metal, by definition, Gauss's law will reinforce the idea that there's no enclosed charge inside any Gaussian surface drawn inside a metal. Because no matter where I draw this surface, the electric field inside the metal is always zero. Therefore, the right side of this equation is always zero. So charge enclosed will always be zero no matter what type of Gaussian surface you have. Like I said, we always apply the rule that the electric field inside a conductor is zero first. It is the first truth about electronics when it comes to using conductors in any discussion. The electric field is always zero inside all conductors. And it doesn't really matter what's happening outside the conductor. If I have a strong positive charge outside the conductor, creating an electric field in the space around this conductor, and even though there's electric field emanating from this conductor in all directions, inside this conductor, the electric field will be zero, regardless of the presence of this outside charge and outside electric field. What will happen is the charges that are available on the conductor will rearrange themselves so that the electric field inside the conductor remains zero. This is a powerful effect inside all of electronics. So in the case of this particular problem, negative charges from all around this conductor will move towards the positive charge that's outside, revealing positive charges on the other side of the conductor. This will create an electric field inside the conductor that opposes the external electric field, creating the conditions to always have an electric field of zero inside a conductor. In all situations in which you have a conductor, the electric field inside the conductor will always be zero, regardless of any outside influence. The charges will always arrange themselves in such a way that the electric field inside will be zero. Now, I've tried to repeat that about 36 different ways, But I don't know that I can emphasize that enough. So let me say it one final way. No matter how powerful the external electric field, there will be sufficient free charges in a conductor to create an opposing field so that the electric field inside the conductor is zero. Again, no matter how strong the external electric field, there will be sufficient charges in the conductor to arrange themselves to create an opposing electric field so that the net electric field is zero. All right, so if you're trying to get to edge or corner cases here, you won't find them. But go ahead, Jeremy.
I don't know if edge or corner means literally like on the edge or corner of that, or if it means exception. But like, what if you have something that like just doesn't have enough electrons to counteract an external charge? Will it just take electrons from its surroundings, or like is that just not possible?
So let me make sure I understand. Is it possible to have such a strong electric field externally that your piece of metal does not have enough electrons to counter the electric field?
Yes.
So the short answer to your question is yes, it will have enough charges. Now, I know that you're going to say, well, no, that can't possibly be possible. You forget, for one, that there's quite a number of electrons in almost every atom. Even metallic hydrogen, if you have a sample of metallic hydrogen or solid hydrogen, even though it only contributes 1 electron per atom, there's a lot of atoms there. And even though the charge per electron is really small, you don't have to have very much hydrogen to have an Avogadro number worth of electrons available to you, which far and away surpasses this amount of charge per electron, getting you, even if you have 1 mole of hydrogen, we're talking a lot of coulombs, right? Order of magnitude 10 to the 4th. So thousands of coulombs of available charge. So you're saying, so what I want to impress upon you is there's a lot of available charge inside metals. Most materials, as you guys are aware, are neutral. And nature abhors the collection of charge in any one place. So for all intents and purposes, there's never an exception to the rule that there will be enough charges inside your metal to provide an electric field of zero inside the metal, regardless of your external electric field. Now, what would happen if we could create Jeremy's condition? Because Jeremy's always trying to get to the edge case. And yes, that's an edge case. You destroy the metal. That electric field would be strong enough to vaporize whatever sample you have next to it. It would no longer be a contingent metal. It would be individual atoms. You would rip them apart. The electric field would be powerful enough to destabilize any van der Waals forces holding that solid together. That's the kind of size electric field we'd be talking about now. You'd probably go from having an object that was a solid to something more akin to a plasma, where you've ripped the electrons away from their source atoms. So the answer to your question is no. In nature, that doesn't happen. Now, I don't know that you can create the conditions for it to happen or not. Well, that's an answer that's just not out there. I am confident, though, that in all the problems we're gonna encounter, we assume that you can't reach that kind of external disturbance. Yeah?
If I had a
Answer to Kyle's question, we're going to talk about the sphere problem in a couple of different ways. And it is usually the first question that students tend to come up with as we talk about the idea of conductors. So it's an excellent question, and I would encourage you guys to pay attention to these 3 or 4 different kinds of ways to answer it, okay? So first, let's consider the case of a solid conducting sphere. First, I want you to be aware that you can have a neutral sphere or a charged sphere. In either case, a conductor can either be neutral or charged. A charged conducting sphere merely means that you've either added electrons to it or taken electrons away. I don't believe I need to state this, but in case I do, charging an object is the manipulation of electrons. Does everybody understand why that has to be true? If not, I will explain it. The manipulation of electrons is possible under regular energy circumstances. You can't manipulate the number of protons because the number of protons is fixed by the atom. The only way to manipulate the number of protons is to change the atom itself. But stripping away or adding electrons to an object doesn't change the atom itself. So whenever we talk about charging an object, we are talking about manipulating its electrons because they're accessible to us. They're not in the nucleus. Now, I assume we'll come back to how many joules an electron volt is after we've discussed voltage. But to kind of make a comparison, that's the amount of energy required to take a single electron away from hydrogen. Now, obviously, the bigger the atom, the more difficult it might be to take some of the electrons away. But keep in mind, the bigger the atom, the further away the electrons are from the nucleus generally, and outer shell electrons can sometimes be much easier. This particular electron is an inner shell electron on the hydrogen atom. You're removing it all the way and stripping it from the atom completely, not just raising it to another shell. To remove protons, generally in the mega electron volt range or higher. You have to smash an atom together to kind of get a proton out. And you can do it to big atoms. Like uranium, plutonium, you can give them a good solid hit, and you can sometimes knock a proton out. But it takes, we're talking huge amounts of resources. The difference between these, of course, is 6 orders of magnitude more energy to try and manipulate a proton, and you have to do so with an atom that's already relatively unstable. So we don't manipulate charges by manipulating protons. And there's another couple of reasons. You change the number of protons on an atom, it no longer behaves the same way it was behaving before, right? If I take one proton away, the atom is no longer whatever it was before. It's something new. And its chemical appearance changes. You guys know all that from chemistry, right? So the process of charging is always the process of manipulating electrons, always. And we don't charge by changing protons. So if you want to make something positively charged, you strip away its electrons. You want to make something negatively charged, you add electrons. For a sphere, a conducting sphere, when you add or take away charges, the remaining charges distribute themselves uniformly around the outer surface. So if I add electrons to this sphere, those electrons will distribute themselves uniformly around the outer surface. That will change if there's an external electric field, but generally, let's say I make this a negatively charged sphere. Then those extra electrons will be distributed uniformly around the outside of the sphere. This will perpetuate the idea that inside the sphere, the electric field will remain zero because the charges will have to be uniformly distributed so that the electric field inside remains zero. Yes, Jeremy?
Are the charges on the surface of the sphere just the additional charges you added, just the additional electrons that is making it charged?
No.
Or is it just all the electrons?
All available electrons that are not bound tightly to their atom will move to the outer edge of any metal.
And is that only when it's charged?
No.
Or is that always?
It has to do that in order to maintain an electric field of zero inside the conductor. So all free electrons in all metals move to the outer edge of the metal in order to preserve the fact that the inside the metal has an electric field of zero. Okay? If you guys don't understand why I'm willing to say that 3 times in a row, it's not for Jeremy's effect that I'm saying that 3 times in a row. In all metals, there is a surface charge. That surface charge can be positive or negative depending on the metal itself, whether it's positive or negative. But all available electrons move to the outer edge of a metal in order to preserve an electric field of zero inside the metal. Conductors behave this way, but I'll remind you that the prevailing fact is that there will be an electric field of zero inside the metal. So that brings us to the idea of what was asked. What about if? And we start getting these if cases. So I create a cavity somewhere inside my my metal. Will the electric field in there be 0? Well, Gauss's law answers this. First, if I create a cavity inside the metal, I can use Gauss's law immediately to discuss the effect of this cavity inside the metal. I could draw a Gaussian surface on the inside of the cavity. By definition, this Gaussian surface will have to obey Gauss's law. How much charge is enclosed? 0. Now, that alone isn't enough to assume that the electric field is 0, but it's a solid argument that we're unlikely to find an electric field inside this cavity. Because if looking here, there's several possibilities of what could happen, but we know that the surrounding area all has an electric field of 0. Do you think it's plausible there could be an electric field inside the cavity? It won't be. If you create a cavity inside your conductor, if the electric field is everywhere 0, just imagine what happens if you say, take my Gaussian surface and make it right here along this inner edge. Right, everywhere that blue line exists has to be an electric field of 0. Right, because it's inside it's inside the metal itself. So the blue Gaussian surface has to equal 0 because the electric field is 0. Correct? Now, I'm not saying that there's no enclosed charge. I'm not saying that. I'm saying that the flux has to equal 0 here because the electric field is 0 because I'm inside the metal now. Now, if I take that yellow surface and bring it out, and I take the blue surface and bring it in, you realize no matter what, it's going to show that the electric field must be 0 inside the cavity. Because as I make that blue surface get closer and closer to the actual hole, this isn't going to change. And as I make that yellow one get closer and closer to the edges of the hole, that's not going to change. So when I get to the point where they're touching, I should be able to show that the electric field has to be 0. Right there, everywhere inside a cavity, inside any conducting surface. So if you don't buy that argument, because I didn't make it particularly well, I'm not going to care too much. If you have a cavity inside a conductor, the electric field inside that cavity will be 0. Now I'm going to put a big if here in a minute. If there's no charges in there. Now, we could change the entire argument by just putting a point charge in there. Now, if I put a point charge in here, things are going to change dramatically now. Maybe not as dramatically as you think, but they're going to change. There's now an electric field inside the cavity. There has to be. If I put a Gaussian surface around that charged particle, it's going to say there's a charge enclosed. And we know a point charge creates an electric field around it. But here's the thing. There's definitely an electric field inside the cavity. There has to be. But the electric field is still 0 inside my conductor, even though there's an electric field inside the cavity. So, like I said, even though there's a charged particle contained in the middle of my conductor, inside the conductor, the electric field still has to be 0, which tells you something important here. If I put a charged particle inside the cavity, inside a conductor, I'm going to be changing the orientation of the charged particles everywhere inside that conductor to ensure that the electric field stays 0 in the conductor. Let's look at a more symmetrical example. All right, this is a super common AP exam question. I have a conducting shell surrounding a point charge, okay? And let's make some kind of definitions. Let's say that I have an inner radius of A and an outer radius of B, and let's say that this is charge Q. All right. If the shell is a conducting shell, then by definition, the electric field here has to be 0. All right? Can you guys use Gauss's law to figure out what the electric field must be for R less than A, R between A and B, and for R greater than B? Do so. This should not take you long. I think this will take you about 30 seconds. Shouldn't have been too hard. There's not a whole lot to do. For this one, the electric field, 1 over 4 pi epsilon naught times Q over R squared. All right. I mean, I would just have chosen the Gaussian surface that's here, and I would have made sure that it was concentric. For, say, this one, it has to be 0. It's inside the metal. It's in the conductor. And for this one, electric field is going to be 1 over 4 pi epsilon naught times Q over R squared. The rules still stand. If I have a conductor, unless the conductor is charged, I would make this my Gaussian surface. What's my charge enclosed? Q. How far away am I? Here. Now, you might say, well, does an electric field penetrate outside of your material? That's a reasonable question. So how do you know this is true? Well, think about what must happen for our second answer to be true. So I want you to just think about this one right here. For the electric field to be 0 in this range, that suggests I probably would have used a Gaussian surface that is, I don't know, somewhere inside the conductor. Does that work? So when I choose that Gaussian surface, that is, I don't know, R, we know by definition that the electric field has to be 0 inside the conductor. We apply that first, which means this part is 0 regardless of what we might want it to be, which means at the same time that Q enclosed has to equal 0. Well, we are enclosing a positive Q. The only way my Q enclosed can be 0, knowing there's a positive Q at the center, is if I have moved enough negative charge so that along the inside edge of my conductor must reside a total charge of negative Q, spread everywhere around that surface.
So all the charges add up to negative Q?
Has to be. On the inner edge of my conductor. You hearing me, Kyle? I mean, you could go further. You could say that the charge density on the inside edge of this conductor would have to be negative Q over 4 pi A squared. Right? The total charge on the inner sphere, which is the inside edge of the sphere, divided by the surface area of that sphere, would be its charge density. So there would have to be a surface charge density there equal to that in order for the total enclosed charge to be 0. Excess charges all lie on the edges of a conductor. Yep.
So would you need a positive
outside of the.
The only way that would work is if that leaves a positive charge of Q on the outer surface of my same conductor. Which is why if I choose a Gaussian surface now that is bigger than my sphere, I'm going to have a enclosed charge of Q. If you want to cancel this, if you want to cancel out the Q that's here with all these Q's on the outside, fine, but then you still have an outer charge density. On the outside edge of my sphere, it's got to be positive Q over 4 pi b squared. There still has to be positive Q now spread around the outside edge of my sphere. That has to happen so that inside my sphere, I have an electric field being generated that is in the opposite direction of the field that's being created by the charge at the center. So that inside the electric field is 0. That can only happen if there's a positive charge around the outside and a negative charge around the inside. Which is why if you consider this surface right here, there must be electric field lines emanating from it because of the concentration of positive charges on the outer edge of the conductor.